Hello friends and welcome at my channel. Let us talk today about a new topic. I would like to start a playlist considering Taylor series. So what is the basic idea behind Taylor series and why do we need it? Well, you see, most of the functions that we're working with are actually not differentiable and well, also a lot of functions that we are working with are not easily integrable. So they cannot, we have no original function easily computed for many cases. And well, that's the reason why we have to somehow replace our, well, maybe difficult, very sophisticated functions by very simple approach through polynomials. So this is the idea. Okay, so imagine you have a differentiable function f of x. Okay, we need differentiability. There are Fourier series where it's not even necessary for the function to be differentiable fully, but we'll come to this in one of my future lectures. But today let's stick to f of x, which is differentiable, and we would like to approximate f of x by a polynomial of degree of n. So something like that. All right, and we keep on going. We have a n minus 2 times x to the power of n minus 2 and so on and so forth. And then at some point we are at, let's say, a4, x to the power of 4 a3, x cubed, then a2, x squared, a1, x to the power of 1, and a0, which is just an absolute value without x. So imagine it would be possible, okay? Just replacement of a function by a polynomial. That would be nice because polynomials are always differentiable, but they're also always integrable. So if we have problems with integrating e to the power of x squared, we have no problems in computing derivatives, right? This is just a chain rule, so it's easily done. But we cannot, maybe in one of my future videos as well, I will prove that there is no original function for these reasons computed just by hand. So in other words, you cannot give me a function capital F of x such that the derivative of this one would give us e to the power of x squared. Simple as that. All right. So if that would be true, so if I could replace f of x by this polynomial, if I could approach it, what will happen if I compute f of 0? F of 0 is, well, you see all the expressions where we have at least one x value would become 0, and the only remainder is a0. So that's nice. I mean, I have a function f of x, I just put in 0, and I already know a0. Well, that's okay. That's a good start. Now let's compute the derivative of f of x. So we have to assume that this function is differentiable. And what will we get? Well, we have an, we have also n coming in front, and then we have x to the power of n minus 1 plus n minus 1. We have a n minus 1. Then we have x to the power of n minus 2. There is an n here. And then we have a n minus 2, a n minus 2, x n to the power of n minus 3, and so on. And then we have, as you can see, 4, a4, x cubed, 3, a3, x squared, 2, a2x plus a1 only. We use by this derivative factor rule and power rule of derivatives as well, and sum rule, so kind of many of them. I'll link it to my playlist. if you need some refresh to refresh your knowledge. Okay, so the first derivative at 0. Look at this. What would be the first derivative at 0? And that would be, you see, once again, all the values with x would become 0, so just only a1. So we already know a0 by knowing f of 0, and we already know a1 by just computing f prime at 0. That's okay. Let's keep on going. So what do we have here? What about the second derivative? The second derivative of x would be, now you remember the first one brought n to the numerator. I think you cannot see me anymore. Is that true? Recorder is recording. All right, so let's keep on going. So the second derivative is n times n minus 1. Then you have a n x to the power of n minus 2 here. And let's skip it. So we had 4 a4. Now we have 4 times 3 a4 and x to the power of 2 plus, then we have 3 and 2. That would be just x, and the expression with the previous expression with a1, let's see it here, it's 0. So we got 3 times 2, a3x, a3x, and then we have, I think, let me check it. You see, I'm computing, I'm not remembering anything. I've never done it. 2a2, yeah, that's correct. Okay. So 2a2 we got here. And now if we put 0 into the second derivative, this one is 0. All the other expressions with x's are becoming 0 again, but now we have 2a2. So what do we have so far? Well, we know that a0, it's f of 0. We also know a1 is f prime of 0. We also know now a2 is, well, let's compute it. Let's solve it for a2. This is the second prime at 0 divided by 2. So you see what's happening? We got three terms already here. Well, that's nice. So if we would estimate or try to approach our function up to the second degree, up to x squared, we would be getting so far. Let me stop here for a moment and let me show you an example before we kind of go further and see the whole big idea. Let us start at one example which is easily computed. If we have f of x equal to e to the power of x, well, this is a very important function in mathematics. In many decay or exponential increase processes, it's involved. And we would like to approach the behavior of this function, let's say around 0. So the easiest way to approach it is just to take a tangent line. Okay, so this is just easily computed. And as you can see, the Taylor idea, Brooke Taylor was the follower of Isaac Newton's mathematics in England at that times. And well, of course, all the foundations from Newton and Leibniz with their calculus ideas, all that was needed in order to move it further. So the tangent line was already known to great Isaac Newton and Wilhelm Leibniz, but as you can see, in order to get further, if you don't take it for granted, if you don't want to stop at the linear approximation, if you want to go further to take it as parabola or even a polynomial of higher degrees, you just have to understand more. So if we have e to the power of x, what is f of 0? Well, that's e to the power of 0, that's 1. What is f prime of x? Well, it's always e of x. Let me write immediately here. F second prime is e to the power of x as well. So f prime at 0 is 1 again, and f second prime of 0 is also 1. So what do we know? Well, we know e to the power of x for x around 0. So let me put it clearly. X very close to 0. It would be a0. A0 is, if you remember, this is f of 0. This is a1. This is a1. And that one is not quite a2 because a2 was, if you remember, f second prime at 0 divided by 2. So that means e to the power of x is approximately a0, which is 1, plus a1 times x, so 1 times x, plus a2, which is a half times x squared. So I'm claiming now that this approach is a kind of, well, not perfect because we're just at the beginning of our approximation, but it's a very good estimation and it's better. This is very important here. This is absolutely clear that it should be better than just the linear approximation by the tangent. All right, so let us check it, how it works. So I'm just putting e to the power of x, so f of x equals to exp x. So you see, there you are. This is the e function that we're working with. And now we say, well, you know what? Let's do it step by step. Let me put it t1 of x. This is just the absolute value. So that would be equal to just only 1. You see? Oh, I've done something bad. Okay. Sorry. T1 of x equals to only 1. All right. So you see, well, this is okay at 0. This is really 1. So, but it's not good enough. It doesn't have the same slope. So that's bad. But let's see, what about t2 of x, so kind of second expression, which is, well, you see, it includes 1, but also having plus x. Now you see it's a linear function, it's a tangent line at 0, and this is slightly better. Well, it has the same slope, which is nice, but it also, as you can see, it follows the function a bit longer. So that's a good one. What about our third expression, t3 of x? Well, that would be 1 plus x still, but also we have here plus a half, something bad, times x squared. No, I think it's fine. So this is the next one. And as you can see, we follow the green curve slightly longer and further and better. So this is the idea. We're going to increase the powers and we're going to approximate our f of x better and better all the time. So that's the point. And now we just have to figure out the pattern of what we're doing. So I hope, guys, you can follow me here because I wanted to normally give an example here because I think it's okay. All the proofs in the theory, it's always important, no question about that. But I think it's always very important to understand what exactly we are proving on, or where are we going. And I hope it's just clear, or became clear, absolutely clear now. So now we have A2, the formula here, and if we keep on going, like if we take the third derivative of x, you see we start here, so it's n times n minus 1 times n minus 2, and maybe you see kind of pattern already. We have an still x to the power of n minus 3, and so on. Now if we take this one, 2 is coming now, so we are having 4, 3, 2, and you see I can actually write 1 if I wish, which isn't the case, but I could recognize here 4 factorial. So I have a4, then just x, and then we have 3 times 2 a3 only, which is 3 factorial, by the way, if we compute it. And now, as you can see, if we put into the third derivative the value of 0, once again, all the guys with x's are becoming 0. And we only have 3 times 2 times a3. That means a3 itself would be f third prime at 0 divided by 3 factorial. Have no hidden information anymore. This is what I'm trying to show you. So what about the fourth derivative? The fourth derivative, we write it the Roman numbers here and in parentheses in order to make sure that we understand that this is derivative of x. What would that be? Well, and as you can see, we had n previously, then n minus 1, now n minus 2, and now we have n minus 3. So this is truly the case. an x to the power of n minus 4, blah, blah, blah. And then what we have now is, well, let's come back here. You see, once again, only this guy remains. So also the expression with x to the power of 5 at the beginning would survive with x. So let me put it here. So we would have 5 times 4 times 3 times 2. Well, I don't need to write times 1 times a5, sorry, a5 times x plus 4 times 3 times 2 times a4. And if we take now the fourth derivative and put 0 for x, once again, everything containing x is becoming 0. So what we have is 4 factorial, so I just shortcut these guys, times a4. And that means a4 itself is becoming to the fourth derivative at 0 divided by 4 factorial. And if I keep on going this way, at the end, I would have an equals to the nth derivative at 0 divided by n factorial. So this is the main idea. So if we keep on going like this, we can estimate our function, or we can approximate it almost perfectly. This is just the very first video here. I will show you more. By the series I from 0 to n. And if we say that 0's derivative of x is just f of x itself, and if we also accept that 0 factorial is 1, which you've done if you're a mathematician, then we can write it this way. So this is at some xo, okay, where we start. In my case, it was 0. These were so-called special series, Maclaurin's, divided by I factorial. I have to write derivative number I here. So these are the a values, if you remember. These are these guys. And this is x to the power of I. And I'm claiming if you give me a differentiable function, I can approximate it pretty well by computing this kind of series. And what is also important here, you see, we get better and better here. And also what we only have to know is the behavior of the function at this only one point. And we also have to understand the behavior of the function and its derivatives at this only point. And we can just move everywhere we need. So this is really huge. So I was doing it for 0 now. So I was just not shifting it anywhere else. We will shift it later on to other points. This is no big deal, but let me maybe finish my example and let us increase our approximation, so improve it slightly. So a3 would be, as you can see, f third derivative at 0 divided by 3 factorial, so that would be just 1 divided by 6, right? And a4 would be the fourth derivative divided by 4 factorial, which is 1 divided by 24, and one more, a5, would be 1 divided by 120. So that means our Taylor polynomial of degree of 5, I'll write it this way, would be a0 plus a1 times x plus a2, which is 1 divided by 2 factorial, times x squared, plus a3, which you can see right here, 1 divided by 6, x cubed, plus 1 divided by 24, x to the power of 4, and 1 divided by 120, x to the power of 5. And I'm claiming this is better than what we previously had. So let me check it here. So let us do it step by step again. So T4 of x, sorry, T4 of x would be equal to 1 plus x plus a half of x squared again, but now we said it's 1 divided by 6 times x cubed. Isn't that nice? I think it is great. You see, we get longer, it's longer, better, faster, stronger. It's really way better. So I really enjoy what I'm doing. I hope you can feel it. And well, let's move on. T5 we're doing as well of x would be equal to, well, let's continue. I think I can write it here as T4 of x, yeah, plus what we have is 1 divided by 24 times x to the power of 4. Well, this is really better. As you can see, we follow the green curve way more. Let me put maybe the last one and this one. Now you see the increase of our precision. Okay, and the last one that we computed, and as you can see, we can go on forever. So T6 of x would be equal to 1, no, I'll do it the same way. T5 of x plus it was 1 divided over 120 times x to the power of 5. And this is once again better. Let us take this one out and this one out. So these are the last two. Well, which one is winning? As you can see clearly, the last guy is winning. Why? It follows once again a bit further, and as you can see, it follows way tighter here. So this is the idea. All right. I hope it was clear. Stay tuned. It's gonna be I think a not so short playlist, so we'll find few more videos. I'll give you few more applications. Also, what are we going to be doing if it's not about 0? And then a very important idea is to estimate the remainder. So I'll explain this as well. Thanks for watching. See you guys in the next video. Bye bye.